All right, starting now, we are recording. Just checking. Okay, nothing on the chats I need to cover right at the moment. So you move a couple of windows on here and go to full screen. And what we were talking about when last we left the spaceship Swine Trek was cycling in ecosystems. And the Earth, aside from meteorites and a little bit of space dust, most atoms on Earth get used over and over and over again. Every atom of carbon in your body has been part of the bodies of countless plants, animals, and microbes, quite possibly since the beginning of life on Earth. Everything feeds on other things. Everything gets reused over and over. And we call that cycling. And the big message last time we met was the carbon cycle, which is driven primarily by photosynthesis and respiration. Photosynthesis is what plants do and other autotrophs. That's a word from early in the semester. When they're able to use some really nifty chemistry to harness solar energy and use that solar energy to take carbon dioxide gas, CO2, right out of the atmosphere and convert it into larger and more complex compounds. In plants, that's notably sugars, and then use those sugars as raw material and or as fuel to build everything else that they need. So plants and algae and photosynthetic bacteria take carbon dioxide out of the atmosphere and turn it into biomass. And then anything that eats them, consumers and decomposers, eat them, break down their biomass, burn some of it as a source of chemical energy, and eventually put carbon dioxide back into the atmosphere. Plants take it in, you breathe it out, and it's the circle of life, and it moves us all. Okay, sorry about that. And there can be some extra little loops and side pathways. It's not truly just one cycle, because fires put carbon dioxide into the atmosphere. Anytime there's a forest fire, that burning plant biomass ends up turned into carbon dioxide. Carbon dioxide can be added by volcanoes. Whenever a volcano erupts, a large fraction of the gas is CO2. And then geological processes can remove CO2. Whenever you get a bunch of silicate minerals exposed to the atmosphere, they weather. And thanks, Ian. I haven't even begun to warm up. You haven't heard me try opera. Be good, or I just might. So yeah, as silicate minerals get weathered and converted into clays, that takes carbon dioxide out of the atmosphere. Living things that make hard parts like seashells or coral reefs, those contain carbon. They're the mineral calcium carbonate. So those can lock up carbon out of the carbon cycle, sometimes for very long periods of time. So there's lots of little side loops, but the big one is that cycle between photosynthesis and respiration. And the last point I was making was that the combustion of huge amounts of fossil fuels is quite literally taking carbon that's been locked out of the carbon cycle for many millions of years. That coal in places like West Virginia is on the order of 330, 350 million years old, although some coal's younger than that. That's carbon that's been out of circulation for all that time, and it's coming back on. It's re-entering the carbon cycle. The effect of that is to start temperatures on average to start warming. And this can have a lot of weird effects that are more complicated than just it's getting hotter every day. Global climate is a pretty complicated machine, but we are seeing the effects of this now, and there's no serious debate about that. I'll say one more thing about that. There have been plenty of times in the history of our planet when this sort of thing has happened and global temperatures have been warmer. Back about 65 million years ago, there were dinosaurs grazing on forest vegetation on the north slope of Alaska. Something like click, 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 Eocene, Oligocene transition. 35-ish million years ago, we had no polar ice caps. Sea level was something like 100 feet higher, and the Gulf Coast began more or less where Arkadelphia is now. You'd have a lot shorter distance to drive for a beach vacation, because you could certainly have hung out on the beaches in, Arkadelphia or let me think. What's that town? Forest City had some pretty nice beaches back in the day. I've actually explored the old beach deposits of Forest City, Arkansas. So the climate has been a lot warmer, and Earth has gotten through it just fine. Global climate change is not going to destroy the Earth or life. Earth and life have gotten through perfectly well. It's going to screw humanity over pretty big time. But, we're just one species, and out of many millions. And if we go extinct, that's okay. Something else is going to evolve later. It always does. Right. The hydrologic cycle, that was the last thing we hit. Solar energy causes water to evaporate from bodies of surface water, oceans, ponds, rivers, swimming pools, what have you. And that water enters the atmosphere in the form of water vapor. If parts of the atmosphere cool, that water vapor starts forming droplets, which make up clouds, and eventually those fall out of the atmosphere in the form of rain, snow, hail, fog, and dew, all those things. That water eventually goes back to the oceans. Either it falls right back in the ocean, or it may return to them in the form of surface runoff, notably rivers.
At the same time.
At the same time. And again, you can have little side quests in your hydrologic cycle, because some of that water might leave the active cycle, some of it will sink down into the earth, and ultimately some of it reaches bodies of rock that are porous, meaning they're spongy, and it may stay there for many thousands of years in the form of groundwater, which is what you tap into if you drill a well. Or groundwater may also naturally rise to the surface, and you've got a spring. Water's also locked out of the hydrologic cycle if it falls in the form of snow and doesn't melt, which is how you get the formation of glaciers in mountains, or how you get the polar ice caps on Greenland and on Antarctica. So yeah, there's lots of little side branches, but this is basically the whole cycle in one photo. As the sun heats the oceans, water vapor evaporates. When it's up in the atmosphere, it comes together in droplets. When you get a whole bunch of tiny droplets, you have a cloud. When the droplets in a cloud get big enough, they fall right back down. And there you have it. You have countless millions of water molecules singing, I get rained down, but I get up again. You're never gonna keep me down. I get rained down, but I evaporate. You're never gonna keep me down. Sorry, that little snarky comment about my singing voice only means I'm gonna do it more, just so you know. Okay, now stuff we haven't seen yet. The nitrogen cycle. There's lots of nitrogen gas in the atmosphere. The atmosphere is 78% nitrogen. That's a lot. Oh, thank you, Carly. Your 3 pointers were quite nice too. But nitrogen gas is not a form that most organisms can use. You need lots of nitrogen because you use it in both DNA. Remember, your bases contain nitrogen, and you need it for proteins because those amino groups on your amino acids, you ought to know what those are, those require nitrogen as well. But unfortunately, nitrogen gas is chemically very difficult to break down. Your body can't do it. You can't absorb nitrogen in a form that you can use just by breathing. Be cool if you could, but you can't. But there's 2 main forces that convert nitrogen in the atmosphere into compounds that living things can use. One of them's lightning. Giant electrical sparks in the atmosphere, that much energy sparking through the atmosphere can actually convert nitrogen gas into nitrates, combining it with oxygen into a form that living things can take up. There's a reason why the Vikings knew that Thor was not just a god of battle, but also a god who could bring fertility, because lightning actually does that. Globally, what's probably more important is that there are certain bacteria called nitrogen-fixing bacteria. They're the critters that have evolved the chemistry that you need to convert gaseous nitrogen into ammonia and nitrates, which are forms that other living things can use. And fortunately, there's lots of nitrogen-fixing bacteria in the soil. We have them in the oceans as well. They're everywhere. And they're responsible for taking nitrogen out of the air and turning it into a form that other living things can absorb. That nitrogen gets taken up by producers. If your plants are not growing very well, you might find that you have to start giving them nitrogen fertilizer. And then, of course, the plants are eaten by consumers. So the nitrogen in the form that you need for amino acids and bases ultimately comes from your food. And so that nitrogen gets cycled around among producers, consumers, and decomposers. Eventually, there are bacteria that are in places like soil called denitrifying bacteria that re-release nitrogen gas back into the atmosphere. Okay, so if you were wondering who run the world, my apologies, but it's neither boys nor girls. It's actually nitrogen-fixing bacteria. We're just here because they put up with us. Sorry. And this is cool, and this is an awesome example of symbiosis, a mutualistic endosymbiosis. Endo means it takes place internally. Most plants in a family called the legumes have little lumps on their roots. I think this is soybean roots that you're looking at, and you can see in addition to the stringy roots, you have those round swellings. Those swellings actually have, the plant grows those deliberately and they're jam-packed full of nitrogen-fixing bacteria. The bacteria that live in those nodules are protected. One funny thing about them is that those bacteria are anaerobic. They're poisoned by oxygen. So the plant literally creates this little oxygen-free home for the nitrogen-fixing bacteria to live. And in exchange, the nitrogen-fixing bacteria take air, because there is air in soils, and convert that nitrogen into a form that the plant can use. This not only nourishes the host plant, but fixed nitrogen can ultimately be made available to other plants. So organic farmers, for example, might plant a field full of clover for a year and then plow it under. And that's a natural way of fertilizing your soil, is to grow these nitrogen fixing plants and then plow them into the soil. And as they rot, the nitrogen becomes available for your next crop. So plants that can do that, legumes, all your beans, peas, clover, alfalfa, I mean, also some non-crop plants like mesquite trees and wisterias and things like that. They've all got nodules on their roots like that. And incidentally, a few years ago when I was in the Conway's agricultural co-op store, the farmer's co-op, you could actually buy not just bean and pea seeds, but you could buy these packages of nitrogen fixing bacteria. It was kind of a black powder that you could mix with your seeds before you planted them, to make sure that as those plants grow, they had plenty of nitrogen fixing bacteria right there for them to use. I tried it one year back when I had a much bigger garden, and seemed to work, seemed to be helpful. So like I said, who run the world? Nitrogen fixing bacteria. Yeah, the rest of us are, just kind of here because, we're here thanks to them. Incidentally, round about, what was the year, like 1914, there was a German chemist by the name of Fritz Haber. And one of the problems the world was facing was you can get natural sources of nitrogen fertilizer. People used to mine Pacific islands for their heavy deposits of seabird poop that had built up over thousands of years, and ship that to put on the fields. But the world was at risk of running out. Haber came up with a process where you could react nitrogen from the air with a source of hydrogen. What they use is natural gas to make ammonia artificially by a non-living process called the Haber process, or the Haber-Bosch process, after Haber plus Dr. Bosch, who worked out how to scale up this process and create these big factories. Most of the nitrogen fertilizer that we use in agriculture is made this way. And somebody calculated that something like 1 in 3 people that are alive today are alive because of the Haber-Bosch process. They're one of the ways in which we've enormously expanded the Earth's carrying capacity for humans. The fact that modern agriculture doesn't rely on the biological nitrogen cycle. They're able to use the Haber-Bosch process. By the way, the same process that fixes nitrogen to make fertilizer also fixes nitrogen to make explosives. So Haber may have revolutionized global agriculture. He also made World War I and all subsequent wars a hell of a lot worse than they would have been, because you can use this process to make the feedstock for explosives as well as making fertilizer. any way you want it, that's the way you need it. Okay, so that's how nitrogen cycling works. The last one I'll talk about is the phosphorus cycle. You've got to have phosphorus because phosphorus is important in your friend and mine, ATP, which we talked about earlier, was the main kind of fuel that metabolism ran on. It's also important in DNA because you've got those phosphate groups together with the sugars and the bases making up your nucleotides. And there's various other things that phosphate does that we don't need to get into. In your case, you need it because your teeth contain it. And this cycle goes really, really slowly because the major driving force is rocks eroding, slowly breaking down from solid rocks into, pebbles and ultimately sand and ultimately silts and maybe ultimately nothing by the constant action of wind and water. As that happens, as rocks break down physically and also chemically, they release phosphorus. And when rocks erode, that phosphorus is released. It may end up flowing away in water, and ultimately it'll get taken up by producers, and then those producers get eaten by consumers, and those consumers get eaten by other consumers, and ultimately decomposers decay everything and return that phosphorus, and so on. Ultimately, given enough time, phosphorus will move out to the oceans, and it may stay there for millions of years as part of the layers of sediment that build up on the bottom of the oceans. Those layers of sediment, given enough time, harden into rock, like the sedimentary rocks that you can see all around Conway, like those rock layers that you see if you take Hogan Road out of town to reach US 64. That's all sedimentary rocks. That's ancient ocean beds. And the very slow processes that lift those up, processes of mountain building that we don't have time to get into here, ultimately form new exposures of rock on land, and that returns phosphorus to the cycle. But you can see the cycle runs very slowly. It might take many millions of years for a mountain range to erode, and then for a new mountain range to be raised. That just doesn't happen overnight. Now, you have to put phosphorus sometimes in agricultural settings. You can buy phosphate fertilizer in any garden store. Most of the fertilizer you'd buy is NPK, meaning it's got nitrogen, phosphorus, and K in this case stands for potassium, which is another thing your plants need. And the phosphorus that's needed for agriculture is primarily mined from areas like this. I think this might be in Morocco, that happen to be rich in phosphate-rich types of rock. The rock gets ground up and added to soils. Unfortunately, number 2,796 of the apocalyptic things you have to worry about, world supplies of phosphate rock are not infinite, and they're projected to start collapsing in the next 20, 30 years. Oh dear. Yeah. So once we get the pandemic out of the way and inflation and global climate and college debt and things like that out of the way, there's something else you can worry about. Here's the thing. In modern industrial agriculture, nitrogen and phosphorus aren't really cycled. That's a field in, I think, Iowa. Iowa grows ridiculous amounts of corn. Like they're really big on corn. And I should know, my dad is from Iowa. Like my blood type is corn. And when Iowa farmers plant, they spread a lot of fertilizer on those fields because corn needs a lot of fertilizer. It's a pretty hungry plant. And so each year, farmers spread fertilizer on their fields, probably more than they really need. And the plants, of course, will take up as much as they can, but there's always some that the plants don't use. And that fertilizer that the plants can't absorb ultimately washes out of the soil, and in this case ends up in the water that is flowing out of that drain pipe into the drainage ditch. And that ditch will eventually connect with, a stream, and then maybe a lake or possibly a river. The same thing happens in livestock operations because animals eat a lot and they poop a lot. And poop is pretty rich in nitrogen and phosphorus, which is one reason why manure is good fertilizer if you treat it properly. But if it's not used as fertilizer, it ultimately washes away and ends up in the water supply, ends up in lakes and rivers. Now, here's the thing. If you take a lake and you dump a huge amount of nutrients in there, if you just fill it with fertilizer, that causes a population explosion in the populations of algae and bacteria. So you get these layers of floating green scum on the surface, which you can see in this photo. Now, nothing lives eternally, and algae and bacteria will live, they'll reproduce, they will soak up those nutrients. Eventually, given enough time, they'll die, and they'll rot, and they'll sink to the bottom. The problem here is that decay, the rotting process, consumes oxygen. So if you have a lot of rotting algae on the bottom of a body of water, the bottom water becomes depleted in oxygen, ultimately so oxygen depleted that nothing can live in it. If you've ever seen a lake do this, you're quite likely to end up with a fish kill. Don't know if you've ever seen one of those, if you've ever seen a lake that just had a whole bunch of dead fish floating in it. That can happen. And we call that eutrophication. Troph is again a root meaning to feed, and eu is Greek for good, but here it means true or real. So if you're really feeding that lake with a whole bunch of fertilizer getting dumped in, tons of nitrogen and phosphorus, you're really feeding it. That's what eutrophication means. And I guess it's a good thing if you're algae. It's not a good thing for most of the life in the lake, because below the surface, you end up with oxygen poor water, and a lot of lake life can't survive in it. So you can end up with a lot of dead fish in your lake. And you can end up with a lot of dead fish in this lake. Let me see here. This is an aerial shot of Lake Erie. That right there, I believe, is Buffalo, New York. That's Erie, Pennsylvania. That's Detroit right there, I do believe. Let me see, I think that's Toledo, and that's Cleveland right there. So there's pretty major cities. This little zone up here, that's actually Canada. Right there. And so yeah, Lake Erie is one of the 5 Great Lakes. And a lot of Indiana and Ohio and Michigan, the parts that aren't big cities, are agricultural countries, agricultural land. And the cities also have a way of discharging sewage that ultimately ends up in the Great Lakes. And so what you're getting is eutrophication on this enormous scale where the lake gets this big input of nitrogen and phosphorus. Some of it's runoff from fields and some of it is sewage. And that causes these periodic blooms of algae that are so big you can see them from space. All of this green stuff right there, right, is a big blob of algae looking kind of like that picture I just showed you, except this blob is big enough that it spans Ohio and Canada. And a problem that results is some of these algae, as they grow, they produce poisons, they produce toxins. And in August 2014, Toledo, Ohio normally gets its water from the lake. They had to shut off their water supply temporarily because there was so much algae in their water supply that it was getting dangerous. Someone asked, why are they called Great Lakes? They're really big. I can't remember exactly how they stack up, but they are some of the largest lakes in the world. I mean, I've walked on the shores of some of them and it really feels like you're on the shore of the ocean. You can't see the other side. They're really big. They're very important industrially because a lot of shipping goes through the Great Lakes. You can sail ocean-going ships all the way to Minnesota if you go up the Great Lakes. And they're an important water supply for all of these industrial cities on the shore, like Detroit and Columbus and Cleveland and Erie and heck, Toronto. And yeah, when the city of Toledo had to shut off its water supply, 400,000 people temporarily had to go without water. And that's a result of eutrophication. That's eutrophication that was so big you could see it from space. There's a lot of nutrient-rich water that drains into the Mississippi River because every drop of water that falls between the Appalachian Mountains and the Rockies, from Pennsylvania all the way to Montana, ultimately will drain into the Mississippi River. It'll, you know, raindrops will fall on the land and soak into a little creek, which will flow into a little stream, which will flow into a small river, which I don't know, might flow into the Arkansas River, which flows into the Mississippi. It all gets funneled down the Mississippi River. And so fertilizer that gets dumped in places like Iowa, if it ends up in the Mississippi, it ends up flowing into the Gulf of Mexico. And what's shown in red right here is this zone of eutrophication. This is water that's so loaded with fertilizer that you have these big blooms of algae. And that might sound nice, but the algae live, they die, they sink to the bottom, and the decay of those algae consumes the oxygen. So we have this zone of the Gulf of Mexico that's called the dead zone, where not very much can live. And the dead zone has gotten larger, and it is potentially a threat to commercial seafood fisheries, because the US gets about 1/3 of its seafood from the Gulf of Mexico. If you don't know, New Orleans is right there. Houston is right there. This is Texas. Like Biloxi, Mississippi is right there. There's Mobile, Alabama. The town where I was born is more or less right about there. That's Lafayette, Louisiana. Raging Cajun all the way. Booyah. So these are the kind of problems that you get when eutrophication comes into play. I don't necessarily have an awesome solution. That's, you know, your generation's job, but it is a potential problem. And it ultimately results from inability to balance nitrogen and phosphorus cycles. All right, check the chat for a moment. Really? Okay, cool. All right, we'll talk about that later. Because my dad taught math and my mom taught French at University of Louisiana Lafayette for many years. They've retired now. That's neat. I did not know that. Okay, right. You hear a lot of talk about organic food, you know, things being organically grown, organic farming and all of that. And there's a lot of claims that it's better for you. The jury is kind of out on that, but a number of studies have shown it's not necessarily better for you. There probably is a good case to be made about not eating too many of the pesticides that get sprayed on food these days. But the real definition of organic farming and organic agriculture is that you try to take every one of those one-way flows and bend it around into a circle. So if you're a conventional farmer, you buy nitrogen and phosphorus fertilizer, you spread it on your fields. Some of it goes into the corn that you grow and you sell that and maybe burn the rest or burn the stubble or something like that. Some other of that fertilizer gets washed off your fields and ends up going down the river to the Gulf of Mexico. It's a straight line shot. If you're farming organically, what you're trying to do is keep those nutrients cycling through the local ecosystem. So the inedible parts of your crop don't get burned, they don't get discarded, they get composted. And if you pile that into a compost heap and let those things decay, the nitrogen stays in the compost heap, and then you can add it right back to your fields for another generation of plants to use. So organic farming is all about trying to keep nutrients from going in straight lines, kind of the same way recycling is. Instead of buy something, use it, throw it away, ends up in a landfill. You buy something, use it, and then reuse the materials to make something else. You keep things going around in a cycle. And yeah, organic farming is basic. Modern organic farming started when somebody looked at a forest and said, hey, wow, how come we never have to fertilize those? Well, the answer is that in a forest, nutrient cycling is going on all the time. Dead leaves fall and they rot, and they're broken down by decomposers, everything from little insects to fungi and bacteria. And eventually the nutrients that were locked up in those leaves get picked up and absorbed and reused by new generations of trees. So that's why nobody ever had to spread fertilizer in a forest. Within that forest, most of the nutrients get cycled over and over and over again. And what makes organic farming good for the earth is that it mimics what the earth is already doing in taking those straight line paths that nutrients would otherwise take and bending them into circles. Using the power of natural cycling, going with the flow. Dude, I sound totally Californian, man. Whoa, is that the Grateful Dead? Cool, but it works. And that's the last thing I've got for you right now. I think I said this was going to end a little bit early. You're welcome. So everybody be careful. Thursday is a bad day for turkeys. So yeah, be careful about that. I will now stop the recording.